All right, so today what we're going to do is we're going to finish, oh, hang on, I have to plug in this camera.
Wait, yeah, okay. So we're going to finish the Markovnikov addition of water to the terminal alkyne. The first part of it, like I said, you use an acid reaction, which is similar to the way that the alkene reaction works, only with an alkyne you need this mercury sulfate salt. And I think it's important to recognize that you do make an enol, which has the alkene as well as the hydroxide and the hydrogen added to the more highly substituted carbon and the less highly substituted carbon, because this shows the Markovnikov addition. But the enol isn't stable and it undergoes a process called tautomerization to make a ketone. And that's an acid catalyzed process, and we're going to go through the mechanism of tautomerization. And then we'll finish up this chapter, should be pretty quickly for this lecture, and then we can start reviewing for your exam, which is tonight at 4. So are there any questions before we get started? Okay. So erase this and start. Okay. So where we're going to start, this is the mechanism for acid catalyzed tautomerization. And this tautomerization, remember, is going to be, in this case, it's going to be specific to the acid catalyzed with the mercury sulfate Markovnikov addition of water. You will also have a base catalyzed tautomerization, but that will be for the anti-Markovnikov addition of water to the alkyne. So in our first case here, we'll have just showing the R group as anything right now. And again, it's important to recognize that this is a terminal alkyne, because if it's terminal, that's the only way you can differentiate between the two carbons, one being secondary, one being primary. And in the conditions of sulfuric acid and water with the mercury sulfate, you make your enol. Okay, and we're going to put it in square brackets because it doesn't last long. Okay. Now, this species is going to then react with acid. Okay. And we're going to use, oh wait, oh no, that's right. Okay, sorry, I got confused. Our pi electrons to get a proton. And then we're going to kick off water. All right. Sorry, all of a sudden I'm very confused about this. Okay. Oh, never mind. Okay, so what we're going to do then is we are going to generate this species. Okay. So what we've done is the proton here adds to this proton here, this carbon. Okay, so H to carbon. Now, if you remember your resonance rules, a resonance structure is going to be more stable when all of the atoms have an octet. So, or a stronger contributor. So this structure does have resonance with this structure. Now, it does seem like it would be better to have a carbocation than an oxygen with a plus charge. But this structure, all the atoms have the octet. So the octet is more important than the charge. This species then reacts with water in deprotonation. To get rid of that positive formal charge on the oxygen, and then you end up with a ketone. Okay, so this would have been the R side, and now this side is CH3. Now, just as an aside, I want to show you what would happen, or at least draw the products of what would happen if you had an asymmetric internal alkyne. So R1, R prime, and R double prime are different. Now, in this case, these are both secondary carbons. So they're both considered Markovnikov carbons. So when you do the reaction in the sulfuric acid and water, in the mercury sulfate, you're going to make two enols. Oops. So you're either going to have the hydroxide on the carbon that's bonded to R prime, or the hydroxide on the carbon that's bonded to R double prime. So then what you're going to get after tautomerization is a mixture of ketones. And that might be what you have to do, but it is something that you would have to consider, is ending up with a mixture of ketones. All right. Oh, I think I'm going to sneeze. Are there any questions about the acid catalyzed tautomerization mechanism? Excuse me. Okay. So the next one is our hydroboration reaction. So this is still a hydration of alkynes. But now it's hydroboration. Okay. Now the hydroboration reaction is anti-Markovnikov. And the nice part about this one is it's the exact same conditions as the alkene. So there's no difference in what you see above and below the arrow. And again, if you're using a terminal alkyne, you do have a difference in the carbons. Okay, now you are going to go through an enol. It's just that the hydroxide ends up on the primary carbon in the enol in this reaction, whereas in the Markovnikov addition, the hydroxide ended up on the secondary carbon. Okay, and again, this will tautomerize, and it is product favor to form an aldehyde. So the difference again between an aldehyde and a ketone is the presence of a hydrogen on the carbonyl carbon instead of two R groups. So the conditions for this reaction, I should have written them. This is BH3. It's a two-step reaction, THF and sodium hydroxide and peroxide. Okay. Now, just like with the hydration by the mercury sulfate and acid, if you decide instead to do this reaction on an internal alkyne, then what's interesting is that you go through your enol and you get two of them again. Oops. But they both will tautomerize to form ketones. Oops. I knew I needed something there. R prime. So the only way that you are going to be able to make an aldehyde is if you do the anti-Markovnikov addition on a terminal species. If it's internal, you get the exact same products as if you had done the Markovnikov addition or the sulfuric acid, water, and mercury sulfate. So you do end up having two ways to do the ketone synthesis, but you really only get one way to make an aldehyde. Okay, so this tautomerization is base catalyzed, and we're going to do the mechanism for that. And I'm going to erase the formation of the ketones unless there are any questions. Okay. So we'll just go ahead and start with our enol. I'm going to draw it slightly differently than what I have here, only because it's going to involve it's going to involve a carbanion, which we haven't seen a lot of up to this point. So you have your base, which will be hydroxide from your sodium hydroxide. And it will pull the proton off of the alcohol in the enol. These electrons will fall into a pi bond, and so that you do not violate the octet for the carbon, you end up putting the pi bond electrons on the carbon, which is going to make that carbanion. Now the carbanion then will see the water you just formed, and it'll take back the proton. And what you end up with then is your aldehyde. And you get back hydroxide, which is a requirement for something that's catalyzed. So your hydroxide goes into the reaction and comes out the same. But you do have a 3-arrow mechanism in which you do a proton transfer, bring pi electrons to a sigma electrons to a pi bond, pi electrons to a lone pair. And this is highly reactive. That carbon doesn't like to carry the lone pair and a negative charge, so it will do the proton transfer reaction fairly quickly. So now the next set of reactions, there's no mechanisms. It's just keeping the product formation for the alkyne set separate from the product formation for alkenes. And some of it has some stoichiometry. Is there any questions about what a tautomer, wait, that's the wrong word, tautomer is, what tautomerization is, or how either the base catalyzed or the acid catalyzed process works? Okay, right. So the next reaction, this is in 10.8, so we're moving quite along through this chapter, 10.8. This is halogenation, which is addition of X2. Okay. And again, we're going to just use chlorine and bromine. But what we have to be careful of is you have to watch for your stoichiometry. And what I mean by that is if you have an alkyne and you write that you're using X2, and in this case the solvent is given, it's carbon tetrachloride. But if you only have one equivalent or you have no stoichiometry shown, then the assumption is that you're going to make a mixture of alkene products with respect to your X groups. The X will be trans, or you're going to make, and you make both of these products, but the other option is that the X's would be cis. Now you can't use the words cis and trans for these, and the reason is because in this case, what I have shown is that you're making tetra-substituted alkenes. So you'd have to name these as high-low and EZ. But with respect to the placement of X, you'll get a trans product and a cis product. The trans product is the major product, but the mechanism for this is not well understood. So it's just important to note that if you only have one equivalent, and that means molar equivalent. So like if you have, like 1 millimolar of alkyne, then you would have 1 millimolar of chlorine or bromine. If you only have one equivalent of your halogen, you stop with an alkene dihalide. If instead you take that same reactant and you either write 2 X2, or you could write excess X2. So it just means that this is in significant concentration so that the halogenation reaction occurs twice, and then you would end up with a tetrahalide like this. And then you'd only get this one product. All right. And again, neither of these mechanisms are well understood. So for this section, it's really just paying attention to the stoichiometry in order to determine where you stop. All right, are there questions about this 10.8? Okay. All right. 10.9. This is oxidative cleavage. And one of your classmates asked me essentially a vocabulary question. Oxidative cleavage is known as ozonolysis. So technically, the reaction is called an ozonolysis. The kind of reaction it is called oxidative cleavage. Okay, and there's only, you know, two things you have to pay attention to. The first one is if it's internal, or the only thing is if it's internal or external or terminal. Okay. And in the case of alkynes, in some ways it's very similar. You have your ozone reactant, and then you have your DMS, which, oh wait, sorry, this is water. Just need to have a mild reducing condition. And you still break apart your alkyne. But instead of making a carbonyl compound, what you're going to end up making is carboxylic acids. Okay. So you get two pieces, both carboxylic acids. If it's terminal though, and you do the same reaction, then when you break here, this, I would call this the inside piece, and this would be the outside piece because of the presence of that terminal proton. So the inside piece becomes a carboxylic acid. The outside piece is released as carbon dioxide. Okay, so this would be a gas, but both of these are considered a product. So even though this is going to be like lost in your reaction, and you're going to reduce the number of carbons in your reactive compound, you can't ignore this carbon dioxide. If you do ignore this, you're going to violate the law of conservation because you're going to have lost a carbon. So when you have an ozonolysis reaction, it's important to remember that whether or not you're going to get all of your carbons into carboxylic acids or release one as carbon dioxide. All right, are there any questions about anything so far in chapter 10? Those are the reactions of alkynes that somewhat mirror the reactions of alkenes. The last part of this chapter is talking about the acidity of alkynes, which goes back to that aereo consideration that you use when you determine stability of bases. Okay, so erase this. Okay, so this actually is not taught at the end. It's in the, let me say that differently. In the book, this is an early section, like 10.3, but I teach it at the end so that you go from alkene reactions to alkyne reactions, which sort of mirror one another. And then we bring in this later bit, which is specific only to the alkynes. So this is called acidity of acetylene. But what acetylene is the simplest terminal alkyne. So this really just then refers to all terminal alkynes. This does not, you don't see any of this behavior in internal alkynes. It's only if they're terminal. Okay, and where we're going to start is looking at the set of 2 carbon molecules. So ethane, ethylene, which is the common name for ethene. You could call it ethene if you wanted to. And then acetylene is the common name for the alkyne. So if we draw our Lewis structures, we're doing this for clarity just so that we can discuss acidity and see the protons that we're talking about. So what we have then is a pKa for all of these species, and it's really just talking about if you lose one proton from each of the compounds. So the pKa of alkanes is around 50. Some of them can be higher, but it's about 50. The pKa of ethylene is 44. The pKa for acetylene is 25. Okay. Now, this is a fairly significant jump because it's important to remember that a difference of 1 pKa unit is equal to a 10-fold difference in acidity. Okay. Where that becomes really impressive is if you look here, because this is a difference of 19 pKa units. So that means that acetylene is 10 to the 19th times more acidic than ethylene. That's a massive number. So this becomes actually very, very useful. Okay. So what we're talking about is taking our acetylene compound and putting it into the presence of a base that has to be strong, like super strong, okay, so that it can remove a proton and make a carbanion. This species, oh, and you'd form the protonated base. Okay. This species, when it comes off of acetylene, or is as a result of deprotonation of acetylene, is called the acetylide anion. Now you could write acid-base reactions for all three of these species, but the reaction is only synthetically possible using acetylene. So our question has to be, why does this work for acetylene or terminal alkynes and not alkenes and alkanes? Questions so far? Okay, so if nobody has any questions, I'm going to take off this lower part, including the pKa's, and just have these three structures and then draw a little bit more underneath. Okay. So the reason why this happens is that it goes back to area. So remember, when you're talking about area, you can use atom identity to stabilize the charge, resonance, induction, and then the O is orbital. Okay. And so what we're going to do is we're going to say, okay, so if we deprotonate, which just means lose a proton from each of these species, you're going to make a carbanion in all cases. But in the case of ethane, you're going to have your lone pair in an sp3 hybrid orbital. Now I'm not showing the little, you can put the little other section there of the orbital, but the electrons are going to predominantly be in the large lobe anyway. In ethylene, the lone pair ends up in an sp2 orbital. And in acetylene, it ends up in an sp orbital. Okay. In terms of the hybrids, as you go in the, ooh, that's a terrible straight line, in this direction, the hybrid orbitals get shorter and fatter as you move in this direction. So what that means in terms of the lone pair is the lone pair in an sp orbital is closer to the nucleus here relative to sp2 or sp3. Okay. Since that lone pair in the sp orbital is closer to the nucleus, and the nucleus, remember, is positive, there's a stability factor in having those electrons near to the nucleus. So this species is possible because of the stability relative to the nucleus of this carbon atom. Okay, so if you remember from the reaction that you wrote to show this deprotonation, you need a strong base. Okay. We're going to look at the reactions that are possible for the deprotonation. So if we take acetylene and we put it in the presence of hydroxide, which is a strong base, and you write the product prediction, you would write that you would make water and the acetylide anion. But remember, when you are asked to judge or gauge position of equilibrium, what you need to know are the pKa's of the acids involved. Okay, so the pKa here is 25. The other acid is the water, and that has a pKa of about 15 or 16, which means that this reaction is left-hand side or reactant favored. Okay. So you need a base that's going to be product favored. And we've seen this base before when we talked about needing a super strong base to do the double elimination to make alkynes. And you can use the amide. And again, you do the same thing. You gauge the direction of equilibrium by the pKa's of the two acids, one on the reactant side, one on the base side. Obviously, this one is still going to be 25, but now the pKa of ammonia is 35. Okay, so this reaction is product favored. Okay. So again, your source would be some sort of amide salt. then you're going to make, in this case, it's called, again, acetylide anion. But if you did this on a terminal alkyne that had an R group over here, it just has a slightly different name. It's called an alkanide anion. Acetylide is just one type of an alkylide anion. Okay. The reason to do this is that the acetylide anion and all other alkanide anions, this group here, these are very strong nucleophiles. Okay. So if you have an acetylide anion in solution and you want to do a substitution reaction, you're going to end up being able to lengthen the carbon chain of the compound you're working with while you retain the presence of the pi electrons. Okay. So this is a very, very useful reaction synthetically, and I'll show you an example of that. Okay. This isn't the only base that will do this. You can use hydride, but again, you'd need like a lithium hydride salt. But hydride is a strong enough base to also do this protonation, although the most commonly used is amide. This one, you're going to end up having to release hydrogen gas, and hydrogen gas is flammable, and you know, it's just one more thing to worry about. But you do make strong nucleophiles, which are very useful. Okay. All right, so I'm going to show you a reaction where we lengthen the chain, and then we will start reviewing for the exam. All right, so let's say we take, oops, can't have double bonds to hydrogens. Acetylide. Oh gosh, can't see it. Okay. And we put this into sodium, amide, and ammonia. Okay. What we're going to make is the acetylide anion, and we'll make more ammonia. Okay, now you could do a mechanism for this. That's not difficult. Oops, it is if you can't see what I'm writing. By just saying, I'm going to go grab this proton and put the electrons on the carbon. Okay, but then you'd end up making your acetylide anion. Okay. Now, let's say you have your acetylide anion, and you have a primary alkyl halide. Okay. In the presence of this compound, and you put this reaction in DMSO. Okay, now this is your nucleophile. Okay. It's a strong nucleophile because you have a lone pair and an anion, and you have a polar aprotic solvent. So this reaction will go by your typical SN2 backside attack, where the carbon from the acetylide attacks the partially positive sp3 carbon in your substrate, and then release bromide. Okay. Then your product becomes this. Okay, so you've gone from two carbon pieces, oops, to one 4-carbon molecule. Okay. that still has a triple bond in it. So you have a lot of options once you get to this compound. Say, well, what can you do with it? Well, this is still a terminal alkyne hydrogen, so it still is acidic. So you could perform this reaction a second time and pull this hydrogen off, make an alkynyl anion on this carbon and do another SN2 reaction. So you can take advantage of terminal alkyne acidity. Oops. What a mess. Okay. But you also have 4 pi electrons in the triple bond. So you have all your alkyne reactions, right? And you have all your alkene reactions. So you could take this compound, and depending on which type of hydrogenation reaction you did, you could either get a cis or trans alkene, and then you can do all your alkene reactions. Or you could make, if you wanted an aldehyde, you could stop here and do the hydroboration reaction and get an aldehyde carbonyl carbon here. You could make a ketone here by using the mercury sulfate in acid hydration reaction. You could put halides on here, you'd get primarily trans, but you would get some cis. You have so many options once you get to this point. Okay. So we're going to use this a lot in chapter 12 when we start putting all the reactions together. Chapter 11 is radicals. That'll go pretty quickly. We should be able to finish 11 in one day. So hopefully tomorrow will just be all radicals, and then the last 2 official days of class would be reviewing reactions in chapter 12, and then we can review whole class content on Thursday. So we're in pretty good shape. Okay, so unless there are any questions about chapter 10, we're done with it, and we can start exam review. Are there any questions? It's kind of hard when you have to have new material taught on a day that it's not tested, because it's really, it seems unimportant, but it's important soon. Okay, so there doesn't seem to be any questions, so we'll go back to review and just quick summary. So exam 3 is tonight. It'll be, again, from 4 to 8 p.m. It'll be on Canvas. It's 25 questions, multiple choice. Each is worth 4 points apiece. It is chapter 7, which is substitution. And chapter 8. And chapter 8 kind of like has 3 parts. It has like an intro to alkenes with naming, cis, trans, EZ nomenclature. And then it has alkene addition reactions. Wait, I lied. Elimination reactions. And then at the end, it's like a SN2 versus SN1 versus E1 versus E2. Okay. The end of substitution is just SN1 versus SN2. But the end of 8, it's comparing all 4. And then chapter 9 is alkene addition reactions. And again, like I said, you had a lot of those, and then they had sort of subcategories as well. So I'm happy to answer any questions that you have. You can either text them in or you can unmute yourself, and we're good to go. If you don't have any questions, we can be done. It's up to you guys. Or we can move on into 11.
Could you review question 11 on the pre-test?
The practice exam?
Yes, that's what I meant.
Okay, that's okay. Let me this one, what is the name of the major product formed?
Yes.
Okay, this one is tricky. It's actually, the reaction is not hard. The problem in terms of this question is that you have to draw the product and then name it. So it ends up taking it another step. But in this reaction, I can't. All right, let me just write the reaction down and go back to my screen. All right. So in this case, HCl, this is a hydrohalogenation. And it adds by Markovnikov addition. So I'm going to draw the mechanism just so we're all on the same page. So the Markovnikov addition means that we're going to end up with our more highly substituted carbocation intermediate. Right. There is a hydrogen on a tertiary carbon. Right. So you would do a hydride shift here. Oops. To make this compound, this tertiary carbocation intermediate, which would get attacked by the chloride. So remember, for hydrohalogenation, if you have, whenever you go through a carbocation, you have to consider that it'll rearrange. Okay, so then my guess is that this is 2-chloro, 2-methyl butane. I hope that's the right answer. Hannah, can you check the key? Is that the right answer? Or do you not have the key out?
Yes, that is the right answer.
Okay. Yeah, so you have to consider the carbocation. Whenever it's made, it has the chance. This, I always try to, in my head, think like, I have to stop here. You can't stop a reaction, but mentally you can stop and say, all right, I've just made a carbocation. what kind is it, and can I make it better? And if you can, through either a hydride or a methyl shift, it will occur. And hydride shifts, you're moving such a small atom that this energy requirement is so small and it's going to happen really fast. So you make this, and then in the solution, it's going to convert to this quickly, and then you'd get your nucleophilic attack. And so this would be considered a major product. But that question on the exam, if you can't write it out, you can't solve it, because this step here, you wouldn't necessarily see without the drawing. Did that help, Hannah?
Yes, thank you.
Okay, there's one in the chat. Number 6, okay. I'm sorry I have to bounce around so much, but it'll work. Okay, so Z conformation. All right, I'm gonna do it on here. Let's make it a little bit bigger. Oh, that's way too big. Way too small. There we go. All right, so again, what you need to do is go in and rank these groups. And first, the way you rank is across, oops, that's not right, across like this. Okay. Anywhere that you have hydrogen is automatically low. This group up here then would be high. Now over here you have carbon to carbon, so they're tied. So you'd have to figure out and make a list of what are the things these carbons are bonded to. So the carbon on the bottom is bonded to 3 hydrogens. The carbon at the top, a nitrogen and 2 hydrogens. Okay. So the nitrogen beats the hydrogen. So this is high and this is low. Okay. Then you draw a line across the pi bond like this, and you find that you have high here, high here. So they're on the same side. So A is Z. So one of the things that you can use for this is if you say it kind of fancy, like French people have fancy accents. Z. Right. If you say it that way, that'll help you remember that Z is same side. So when you were doing this, I think it was Sarah, was there one that you couldn't figure out and you couldn't determine which of the 4 was Z? Did you get multiple things that were Z, or did you not? I guess I'm trying to ask, how many more do you want me to do to solve this problem? Okay, so some things, you know, typically, you should always double check, but typically if you have something with a double bond, it will be high, and something with only single bonds will be low, typically. But you should always double check. And then if you get, there's only ever one right answer. So if you if you have a hard time, just remember, like, if you can't find one correct answer, then you have a mistake in something.
How do you determine like which double bond you're going through?
That's a good question. So for this one, because there's a pi bond here as well, it's the one that is, in this case, drawn flat. Like this one over here is not, this is mono substituted, okay, because you have 3 hydrogens on it, you only have 1 R group. So this one you wouldn't be labeled E or Z, it would only be this one. That's a really good question for that. Let's see. My assumption, if I remember correctly, is that we were asking about this pi bond, not that one. But that would be something like, I'll have to double check. I don't think the molecules are this complicated tonight. But that's a good question. All right, so 13. Oops, I gotta clear all that stuff. Okay. All right. So in 13, so I mean, I can draw it for you if you want it drawn, but you'll have to tell me, Rebecca. So there's just a few things, like I would always like write a few notes before I get started, because if you look down here, it's overwhelming. So if you look down here at first, it's overwhelming. So I would almost like ignore all of the stuff written below, and I would focus just on right now this part, okay? And why I say that is because if you look at the substrate, there's 2 functional groups, okay? You have a benzene ring, and you have an alkene, okay? And then you have to ask yourself, have I learned anything about benzene ring reactions? So the answer is no. So this means you can only do reactions on the alkene part. Okay, so sometimes this isn't the case where that's true, but sometimes you'll see answer selections where the benzene ring has been messed around with. So not in this case, but you would go, that would be a way to mark something off. So you would say, okay, this part of the molecule, this benzene ring on the left, has to remain unchanged from start to finish. And in all cases, that's true. The next thing that I would do is I would look at the alkene carbons, okay, and highlight the ones that are involved. So you have a carbon here to here, which is here to here, here to here, here to here, and here to here. Okay. Your exam, again, this is something that you're going to have to remember, is alkene addition reactions result in substituted alkanes. Okay, you have to lose the pi bond. Okay, so if you look then down at option C, you're retaining the pi bond. So this is wrong. Okay. Then I would look at the conditions. So you have a halogen, or you have a dihalide, but you have no solvent shown. Okay. So no solvent shown means that this is a halogenation reaction, okay, which marks out A, because A is a halohydrin because of the presence of the oxygen. So your last choices are a cis dihalide or a trans dihalide. Halogenation reactions add by anti-addition. So you're going to end up with your halides trans. So that's why it's D. Rebecca, does that answer your question about kind of how to approach these? Yes, okay. So remember, the anti-addition is because you go through like a 3-carbon or a 3-atom cyclic intermediate. So in this case, it would be called the bromonium ion. And the bromine atom that's connected to the 2 carbons is going to take up the entire face, one of the faces of the ring, either the top face or the bottom face. And so then the attack has to come from the second bromide anti to the first. Okay. Other questions? Okay, let's see. 19. Okay. Okay, so let's see, 1-butene was reacted by halohydrin. Okay. All right. So let me make sure that I'm doing this right. Okay. All right. So in this case, it's just really important that you know what the words mean. So halohydrin means that you're going to add a halogen and an OH group. They're going to add anti. But since this is 1-butene isn't cyclic, that would sort of be hard to draw. So 1-butene, oops. This is not going to be my best molecule. Looks like this with a pi bond here. Okay, and then the conditions for this would be Br2. Oh, well, you'd have to say X2 initially, and water. Okay. So, but you don't know the conditions of X2 yet until you look over here. So this 1-to-1 peak height ratio from M plus to M plus 2 plus, I should have these things right. Those aren't electrons in there, that's a ratio sign. Okay, and that 1-to-1 means bromine. Okay. Then when you look at your IR, you see a few features. So you would come down again to 1500, draw your line. So all this stuff over here you can ignore. Then you look and you see, let's see, this, and this. Okay. The first is sp3, carbons to hydrogens. The second is an alcohol, OH. And since you have that alcohol OH, this is most likely free OH. That's not participating in hydrogen bonds. Okay. Okay, so between these two factors, you know that you get a bromine and an OH group on your compound. Halohydrins add by Markovnikov addition. So the hydroxide, you're going to go through a bromonium cation. I'll have to draw this one on the paper, or sorry, on the whiteboard to show you the mechanism. So let me go back. So in this case, you'd go through, let me write it up here. You'd go through this species. So when you look at this, the bromine has a positive charge. So the electrons are going to be pulled in this direction, building up positive charge at a primary carbon and a secondary carbon. A secondary carbon can better carry a partial positive charge. So it'll be a, let's just say, positive plus plus, where this is only positive plus. So then the water will attack here, kick electrons off. You'd make this, that would be deprotonated. Oops, gosh, that looks like a radical. Like that. Andrew, did that help?
Yes, thank you very much.
Yeah, no problem. Okay, so Sarah said 14. Okay, all right, this is, okay, so this reaction, again, I would not look at the products first. I would ignore all of this first, and I would come up here, and again, you have an alkene, and I would highlight my carbons involved, or mark my carbons involved. Look at my reaction conditions. It's missing the tetrahydrofuran, but that's not that big of a deal. I mean, there's only one answer to this. So the BH3, that is a hydroboration oxidation reaction. And that is a type of hydration reaction for alkenes. It's the anti-Markovnikov addition of water to make an alcohol. Okay. Then come down and look at your answer selections. Okay. This is a diol. C is a diol, so that can't be right. Okay. If you look in B and you highlight the carbons involved in the reaction of the alkene, the OH ends up on a carbon that wasn't in the original pi bond, so that makes no sense. So this one has to go. And then when you look at A versus D, they're both alcohols. But in A, the hydroxide is on the more highly substituted carbon from the original pi bond. So this is the Markovnikov product. It's an accurate product if your conditions were acid catalyzed hydration or oh my gosh, the words are escaping me. Okay, and it's the Markovnikov addition product. So this has to be your anti-Markovnikov product, which is D. Oh, oxymercuration will give you this. That's right, oxymercuration. Yep, that's right. So when you look at these questions, if you're struggling to write this stuff up here, of just kind of breaking down these reactions, you need to get those. I would spend some time today kind of working through those vocabularies, because the reactions are so much easier if you can read this with words like that I've typed up here in red. Any other questions? Okay.
Could
Yeah,
you,
go ahead. Go ahead.
Question.
Yeah.
Can you go over and just talk about number 7 just briefly?
Oh, sure. 7 and 8, perfect. Okay. Okay. All right. So stability of alkenes is related to the number of groups. I guess we'd say non-hydrogen groups off the vinylic carbons. So the vinylic carbons are the carbons that are in the pi bond. So then your options, I would describe them in words first. So like up here, I would write that this is a trans disubstituted alkene. Okay. Now, once you get to tri-substituted, which is shown in B, you don't know if it's E or Z. And actually, since these are both indicated as actually methyl, they're both methyls here. So you wouldn't use E or Z here because those would be tied. But regardless, it's tri-substituted. Okay. C is tetrasubstituted. And then D is cis disubstituted. So the more R groups you have, the more stable. So since this has 4 R groups off of it, C is the most stable. So it would be, if you ordered them, C is higher in stability than B, which is higher in substitution or instability than A. Trans is always more stable than cis because of the loss of steric strain. So there's a couple ways questions like this can be asked. You can just get the 4 compounds and then which is the most stable, which is the least stable. But in this set, you could also rank from low to high or high to low. Hannah, did that help?
Yes, thank you.
Okay. And then 8. Okay. All right. So in this case, which base should be used to cause the elimination reaction shown below? Okay, now where I would start this is highlighting, oops, that's a little messy, the carbons in the alkene versus the carbons in the substrate alkyl halide. Okay. Because once you do that, what you're able to do then is classify this carbon here, which is secondary. And there are 2 places where there are protons. This is then, sorry, let me go back. This then is the alpha carbon. And what you would need to know is what is possible on your beta carbons. Okay. So this here is tertiary. This one over here is primary. Okay. So if you pull from the tertiary carbon, you would make a Zaitsev product, the more highly substituted alkene. If you pull from the primary, you're going to make the Hoffman product. Okay. And you know you're going by an E2 mechanism because all of your options are strong bases. So strong bases, so lone pairs and negative charges favor E2 over E1. And in E2 reactions, the size of the base can dictate whether you get Hoffman or Zaitsev. So this is the Hoffman product, and it's only going to be formed as the major product in an E2 reaction with a big base. And so this is 1, 2, 3, 4, 5, 6, 7. That's bigger than tertiary butoxide. 7. I don't actually know what, I'd have to look it up what this would be called, but this is huge. So this is a big bulky base. You have huge groups on the end. You have a 3-carbon group here, a 2-carbon group, 2-carbon group. This is small. Methoxide is small. Ethoxide is small. Now this is isopropoxide, but it's smaller than this. So you would pick the biggest, strongest base to give you the Hoffman product. Carter, did that help with 8?
Yes, ma'am.
Okay, thank you. All right. Any others? We can scroll through them and see if there's things that come up as we look. I gotta make it smaller a little bit. I can't. There we go. Okay. All right. So 1 is okay, and with recognizing substrates for SN1 versus SN2. And if you have questions, just text or chat or unmute yourself. This one is asking you, do you know what mechanism dominates? Okay, so you have a few clues in here. You have, let's see, 1, 2, 3. This is a secondary system, which could go by E1, excuse me, SN1 or SN2. And you know by looking over here that you're not making an alkene. So the alpha carbon is here. You don't have a beta hydrogen down here. You have a beta hydrogen here, but neither of these products has an alkene in it, so it cannot be elimination. You're shown the mixture that you get 100% of one enantiomer, 0% of the other. You have a strong base and polar aprotic. So this is all leaning towards SN2. This third question is about solvent identity. What works for a specific reaction? You have to recognize that this is secondary. We're using tosylate as the leaving group with a strong nucleophile. Getting a mixture of products, though, means you have to have a carbocation intermediate, so you can get iodide attack from the bottom as well as the top. So you would go by SN1, which would need a polar protic solvent. Okay, 4 is recognizing when you can or cannot, with the identity of the substrate, undergo substitution. So this is an alkyl halide. This is a vinylic halide. Vinylic substrates don't go through substitution reactions at all. This is recognizing that just correct arrow flow. So you have to go from electrons to atoms. And this is a tertiary substrate, so you can't have nucleophilic attack until you've made a carbocation intermediate. So 6 we did with E or Z, 7 we did, 8 we did, 9 we did not do. You're told it's elimination. So even though you saw tosylate as a leaving group in substitution, if it's a good leaving group, it's a good leaving group. So in this case, the tosylate is the leaving group. On the alpha carbon, you have a small base, so you would make the Zaitsev product. Yes, so YB is wrong in 6. Okay, so let me just finish this up next. So this one is an elimination reaction to make the Zaitsev product. Strong small bases go by E2, so that would be C. So 6B, okay. You have to use this one, I think. Let me do this one. Okay, so first we go here to here. Okay, so carbon to carbon, C, C, C. So this up here is high. This one is low. Carbon to carbon, that's right, HHO, HHC. So high is down here, low is up here. So then they're going to be on opposite sides. Now, this one is a little bit weird because you do have another pi bond, so we must have had to, when we gave this exam, make an announcement to use this alkene. That makes sense, Nick? No, it's not cis, it's E. And it's asking for Z. So this one would be an E. At this pi bond here, it would be E. Technically, you'd have to do an analysis here. I can't, like I said, I'm very sure that last summer we had to announce which of the pi bonds we wanted them to analyze. No, E is not trans. It just means that the lows are on opposite sides. Let me go back to the screen. They're not necessarily talking about the same thing. Okay, so when you have a trans, using the word trans, that means that our groups are on opposite sides of the ring, which means that in a trans system, you have 2 hydrogens. So trans and cis, those are words that you use to relate di-substituted systems. Okay, so they're relative. Trans is a relative word. Okay, so cis and trans is going to be relative stereochemistry. No, it's not Z. In that case, what you have high in E and Z is low, low, high, high. This is E. This is Z. And these are used in tri and tetra substituted. I see where your analysis is. Well, these are on opposite sides. This you just said was opposite sides. The differentiation is that in di-substituted alkenes, you're going to have 2 hydrogens. And in tri and tetra, you're only going to have 1 or 0 hydrogens. So E and Z are used for tri and tetra substituted alkenes, whereas you can use cis and trans for di-substituted. So it's related to how many groups. So that question, okay, all right. I'm not going to make it worse. All right, so 6, 7, 8, 9 we did, 10 we did, or we did not do 10. 10 is asking you the identity of the product after an elimination E2. So in this case, it's kind of tricky to see with everything drawn on here, but you're looking for an anti-periplanar hydrogen. So it would be here, here, here. Okay, now the weirdo is up here, because this hydrogen in green is also anti-periplanar to this iodide. So there are 2 hydrogens that are considered beta and anti-periplanar. But because of the presence of this methyl group, and this is a small, strong base, you are going to make a Zaitsev product. So this is, B and C are what happens if you would use a different base to make the Hoffman product. D is impossible because it's too far away. That carbon, that is not, it would be like a gamma carbon, gamma hydrogen. So it would be A here. Okay, 11 we did. Okay, 12 is recognizing here that you're making a Markovnikov alcohol, and Markovnikov alcohol goes through this mercurinium ion. We did 13, we did 14, we did not do 15. Let's see, so okay, so in 15, you're going from an alkyl halide to an alkene, which means that this is elimination. And if you look at your answer choices, that takes out A and B. And now, in my opinion, I wouldn't spend a lot of time here worrying about whether this is E1 or E2. I just kind of classify them by the star by the broadest category possible. So this is a hydration, but it's a Markovnikov hydration. Okay. So in these conditions, you have acid catalyzed. That's what that's called. You don't do oxymercuration because you don't have a mercury substrate in there, or mercury reactant. So it can't be oxymercuration. The word mercury is in this, standing mercury up here. So then that means it can't be B, so you've eliminated everything down to get answer D, and then it's telling you, well, then it has to be E1. It's not asking you specifically if it's E1, but the answer choices give it to you once you analyze the second step. Okay. Okay, now the rest are write-ins. And so if we just take a look at what's in the write-ins. This is asking about mechanisms. So in a write-in question, can you draw the correct mechanism? In a multiple choice, it would have to be, can you recognize the arrows required in the correct mechanism? So that would be the number of arrows involved and the direction of those arrows. Again, same thing with here. Just can you analyze correct and incorrect arrows? Same thing here, analyzing correct arrows, identifying correct intermediates. In this case, you make the tertiary carbocation, so you don't have to worry about rearrangement. And then, of course, naming is still on the table, as is IR and mass spec. In this case is recognizing what you need. This is like A, B, C. You're given B and C. You need to analyze and find out what the reactant would be. A, B, C. You'd need to figure out what the product is. Simple things like, do you still remember all your functional groups? And then we ended up, okay, so this question, the reason why B wasn't graded is it ended up that grading B made the exam out of 101 points. So we just picked the one because it was so wordy to read. We didn't want to grade that. So that's why it was dropped. And then we did this one. We've already done this one. And then again, recognizing correct arrows. All right, any other questions before? We're not going to use the 8 minutes on chapter 11. We'll just start 11 another day.
I have one more question.
Sure.
This is just more general, I guess, but that question with the IR and mass spec, is that a good example of the type of questions that we would have using that on the exam?
Pretty much, yeah. So at this point, like in the last exam, didn't have a ton of mechanisms yet. So IR and mass spec were still used as like, what is this molecule? And now that you have mechanisms, it might be like, this is the reaction taking place. This is the data for the product. What is the identity of the product, or what conditions were used to make this product? Because like in this question here, you could have answered this without being given the word halohydrin. So that word was added as sort of a little nudge in the right direction. But in theory, this question could be answered without that word, because you'd still come down here to get the bromine and over here to get the hydroxide, and then you would hopefully link that as a halohydrin, and then that word becomes a moot point. But it's still kind of early, so it's a little nudge in the right direction. But yeah, that's kind of where the IR and mass spec will be. And like your questions related to that, it wouldn't necessarily be theory of IR or mass spec anymore, it's gonna be application.
Okay, thank you. That answers my question.
Good. Anything else? Okay, if there aren't any more questions, I'm going to let you go. And as soon as these notes come up, I will post I get the Zoom recording. I'll post it so in case you want to go back and listen to anything before the exam. And I will see you guys tomorrow. All right, have a good rest of your day. It's rainy again. All right, thanks so much. I'll see you guys tomorrow.
Thank you.
Yep.